This aircraft was never supposed to fly, and physics almost proved them right. The fighter jet that physics said shouldn't exist. Hook, the crash that proved the equation right. In the late 1970s, several experimental aircraft behaved in a way that terrified test pilots. They didn't stall normally. They didn't recover naturally. This is where the real engineering began. And sometimes, they simply departed controlled flight. Not because of engine failure, not because of pilot error, but because the airplane itself was aerodynamically unstable. And for decades before that, aerospace engineers were taught one fundamental principle. An aircraft must be statically stable to fly safely. That principle comes directly from Newton's laws. If disturbed, a stable system must produce restoring forces. If it doesn't, divergence occurs. Subscribe for more stories about the machines that changed the world. Now imagine proposing a fighter jet that is intentionally unstable, has minimal vertical tail area, uses wing shapes that reduce lift efficiency, sacrifices aerodynamic purity for radar invisibility, and still must fly at Mach 2. On paper, this shouldn't work, because aerodynamics punishes compromise. And yet, the F-22 Raptor exists, and so does the F-35 Lightning II. This is the story of how physics said no, and engineers negotiated anyway. And that's how engineers bent physics, without breaking it. Part 1: Why it was impossible. The context: the Cold War driver. Visual: radar screen locking onto aircraft. By the 1970s, radar-guided missiles had transformed air combat. Flying faster wasn't enough. Flying higher wasn't enough. Electronic jamming was unreliable. The new requirement was simple: avoid detection entirely. But stealth geometry violates aerodynamic ideals. Let's examine why. Part 2: the physics constraint. The drag equation. Visual: equation appears on screen. D equals \frac 1, 2, \rho v squared c underscored a. Drag increases with the square of velocity. Double speed 4 times drag. At transonic speeds it gets worse, because shock waves form. The transonic barrier. As aircraft approach Mach 1, air accelerates locally over curved surfaces. Pressure drops. Shock waves form. Boundary layer separates. Boundary layer separation means airflow detaches from the wing. Lift collapses. Control becomes unpredictable. Visual: CFD simulation showing shockwave formation. Supersonic aircraft solve this using swept wings, thin airfoils, smooth curvature, area ruling. Stealth requires something different: flat surfaces, hard angles, internal weapon bays, edge alignment. These two design philosophies directly conflict. Aerodynamics demands curvature. Stealth demands facets. Part 3: What failed. Early stealth, the aerodynamic disaster. The F-117 Nighthawk looked like a flying pyramid. Because it was. Its faceted surfaces reflected radar away from emitters. But aerodynamically, it was terrible. Lift-to-drag ratio around 4:5. For comparison, modern airliner, 18:20. Glider, 50. Early stealth, 5. That means for every unit of lift, enormous drag penalty was paid. Why? Because airflow prefers smooth pressure gradients. Facets create abrupt pressure changes. Abrupt pressure changes create vortices. Vortices create drag. Physics is unforgiving. Stability, the bigger problem. This is where the real engineering began. Traditional aircraft are designed so that center of gravity, CG, sits forward of the center of lift. If nose rises, restoring moment pushes it back down. Stealth jets wanted minimal tail surfaces, which means reduced pitch stability. Move CG too far back, the aircraft diverges. It will pitch up uncontrollably. And without computers, that divergence happens faster than a human can react. Part 4: What engineers tried. Solution 1: Relaxed static stability. Instead of fighting instability, engineers embraced it. The F-22 is designed to be unstable. Why? After years of failure, something finally worked, because stability adds trim drag. Trim drag is the aerodynamic penalty paid to keep aircraft balanced. Remove stability, reduce trim drag, increase maneuverability. But you must replace natural stability with artificial control. Enter digital fly-by-wire. Visual diagram showing flight computer correcting pitch oscillations. Flight computers adjust control surfaces hundreds of times per second. Humans can't. Physics didn't change. Control bandwidth did. Solution 2: area ruling with stealth. Supersonic drag spikes when cross-sectional area changes abruptly. The solution is the area rule. The fuselage must narrow where wings widen. But stealth shaping limits curvature. Engineers created blended wing bodies and internal bays. Weapons that were once external, now internal. Triple fuel consumption. Increase infrared signature. Reduce engine life. The F-22 supercruises at Mach 1.5 without afterburner. How? Extremely high turbine inlet temperatures. Visual. Exploded turbine blade with cooling channels. Turbine blades operate beyond melting point. They survive due to single crystal superalloys, internal cooling passages, ceramic thermal barrier coatings. Let's go deeper. Why single crystal? After years of failure, something finally worked. Because grain boundaries in metals are weak points. At high temperature, creep occurs along grain boundaries. Remove boundaries, increase strength. We've now reached atomic-level engineering. Thrust vectoring. Visual. Rear view showing vectoring nozzles. When airflow loses effectiveness at high angle of attack, thrust can provide control moments. Vectoring nozzles redirect exhaust. But, add weight. Increase maintenance. Increase mechanical complexity. It's not magic maneuverability. It's redirected momentum. Part 6. The trade-off. Let's quantify compromise. Speed versus fuel. Kinetic energy. KE equals \frac 1, 2, mv squared. Mach 1.5 versus Mach 1. Velocity increases 50%. Energy increases 125%. Fuel burn rises accordingly. Supersonic flight is expensive in energy terms. Stealth versus maintenance. Stealth coatings degrade under UV exposure, rain erosion, temperature cycling. Maintenance hours per flight hour are high. The F-35 Lightning II was designed to reduce this burden. But stealth still isn't free. Lift-to-drag ratio reality. The F-22 improves L/D over F-117, but still lower than pure aerodynamic designs. Because stealth shaping imposes geometry constraints. Engineering is choosing which loss is acceptable. And that's how engineers bent physics, without breaking it. Part 7. Debunking popular myths. Myth: stealth aircraft are invisible. Reality: radar cross-section reduction is directional. From certain angles, detection range increases. Stealth is probability management, not invisibility. Myth: extreme maneuverability wins dogfights. Modern air combat is often beyond visual range. Missiles with active radar seekers engage targets miles away. Maneuverability matters, but less than sensors. Myth: faster is always better. At Mach 2, drag and heating skyrocket. Skin temperatures rise dramatically. Thermal expansion alters tolerances. Speed is constrained by materials and fuel. Part 8. Why it matters today. The sixth-generation fighter programs worldwide still face the same equations. Drag still scales with velocity squared. Shock waves still form at Mach 1. Fuel energy density still dwarfs batteries. Visual graph comparing battery versus jet fuel energy density. Jet fuel, 43 mJ/kg. Lithium-ion battery, 1 mJ/kg. Electric supersonic fighters are currently unrealistic. Physics hasn't softened. The economic reality. The F-22 cost over $150 million per aircraft. Production stopped early. Why? Because extreme performance was too expensive at scale. The F-35 pursued a compromise. Lower top speed. multi-role flexibility, larger production numbers. Engineering is constrained by budgets, not just equations. The verdict. So did physics say this fighter shouldn't exist? Yes, in the sense that stability contradicted stealth. Supersonic speed contradicted efficiency. High temperature contradicted materials. Maneuverability contradicted structural limits. But engineers redistributed constraints. Computers replaced static stability. Materials science pushed temperature limits. Geometry balanced radar and airflow. It works, but it's expensive. And physics still wins every negotiation. And that's how engineers bent physics, without breaking it. Final thought. Every generation believes it has defeated nature. But in reality, we don't defeat physics. We compromise with it. The fighter jet that shouldn't exist does exist. Not because equations were wrong, but because engineers understood them deeply enough to bend design around them, and that more than speed or stealth is the real achievement. Subscribe for more stories about the machines that changed the world. Computers replaced static stability. Materials science pushed temperature limits. Geometry balanced radar and airflow. It works, but it's expensive. And physics still wins every negotiation. And that's how engineers bent physics, without breaking it. Final thought. Every generation believes it has defeated nature. But in reality, we don't defeat physics. We compromise with it. The fighter jet that shouldn't exist does exist. Not because equations were wrong, but because engineers understood them deeply enough to bend design around them, and that more than speed or stealth is the real achievement. Subscribe for more stories about the machines that changed the world. Subscribe for more stories about the machines that changed the world.